This is an AIA continuing education session and is presented by Mr. Scott Wolff, and the presentation is titled Permeable versus Non-Permeable, Which Decision is Best?
Great. Well, thank everybody for joining us today. This is a bit advanced. I refer to it as a 102 type program. I wrote this program a couple of years ago based on just patterns that I've seen, and it was just sort of out of talking to consultants and architects, building envelope specialists. And so this is sort of a culmination of just information that I've gleaned from people way smarter than me. So it's just sort of based on a lot of available industry information. Objectives today will be to gain a knowledge of correct terminology, definitions, specification language, review material properties of exterior typical wall components. We'll also look at air barrier types, their compositions, and differing reactions to moisture exposure. As with any above grade wall, the goal really is to design for optimum drying capability of the wall. I always say, probably several times throughout, it's never a question of if walls get wet. They're always going to get wet through any number of dry mechanisms. And ultimately, the goal here is to attain a baseline of understanding when to consider permeable versus non-permeable air barrier. So for terms and definitions, what is a vapor permeable air barrier? It's just simply any material that's air and water impermeable, but water vapor permeable, meaning that's going to stop bulk water from getting in and air from getting through. Air barriers certainly are not waterproofing. They are not generally designed to tolerate hydrostatic head pressures. This is sort of a sidebar for something I could go along into because I think occasionally we'll have some confusion on that subject. Vapor retarding air barrier, i.e. a non-permeable air barrier, is any material that is air, water, or water vapor impermeable. I'm holding up a piece of below-grade vapor barrier, as we generically refer to them. This is just one example. Of course, there are air barriers that are either in sheet form or liquid form that are, a lot of them are composed of rubberized asphalt. These are also vapor-retarding air barriers. ASTM E2178 is the standard test method for determining air permeance of building materials, and it just simply states that this individual material will resist air permeance or air leakage at a rate of not greater than 0.004 of a cubic foot per minute at a 75 Pascal load or 1.57 PSF. And E96 is the standard test method for water vapor transmission materials, and that's just simply a standard that evaluates how much water vapor in the form of a gas will be able to migrate through said air barrier material. Water vapor permeance is the time rate of water vapor transmission through the unit area of a flat material or construction induced by a unit vapor pressure delta between two specific surfaces under specified temperature and humidity conditions, again, measured by E96. The term perms is the unit of measure for the amount of water vapor passing through a given material over a period of time. In other words, the U.S. perm is defined as 1 grain of water vapor per hour per square foot per inch of mercury. And what's interesting about this definition here is a water grain or grain of water, it takes 59,000 grains of water to equal 1 gallon of water. I'm presuming most everybody knows the term perms. Grains and perms are roughly synonymous with each other. So if we have a material or construction, an air barrier that is defined as 1 perm or even less than 1 perm, we're not realizing a lot of water vapor diffusing or migrating through that material. That's kind of an interesting factoid that will become more clear as we move on. Vapor retarder is a water-resistant material or construction with water vapor permeance values described in Chapter 2 of the Code. The term vapor barrier, and I wish I could probably put a red circle with a slash through it, is really an antiquated term and I think should be scrubbed from all construction documents. It's technically incorrect. The code defines vapor-resistant materials as vapor retarders. There's no material that is a true barrier. Given two things, pressure and time, all we can expect any of these materials to restrict a certain amount of water vapor. Again, I was holding up a 15 mil below grade vapor barrier. The term vapor barrier is being inaccurate. If we look at some of the technical data for these 15 mil systems that we put under slabs, for example, the water vapor permeance will typically measure out at 0.00011. You can see that's almost a vanishingly low amount of water vapor, but the fact remains that there's still a very, albeit very infinitesimally small amount of water vapor that gets through it. So hence the term, they're retarding water vapor and they're not acting as a true barrier, meaning nothing's going to get through it. The code defines vapor retarders by classification. So a class 1 vapor retarder is going to be the most restrictive and is defined as having a permeance of 0.1 perms or less. Class 2 vapor retarders are less than 1 perm but above 0.1 perms. And then the term class 3 vapor retarders, which I'm not a big fan of because I think anybody that's not getting into the minutia of the code might still say class 3 vapor retarder is something that's vapor restrictive. Well, it's actually defined, I guess, in some terms as vapor semi-permeable, and that'll be above 1 perm but less than 10 perms. So as the code is written, we have to jump around into different sections to figure out what a vapor barrier is, and I'm going to use that term. So a vapor barrier as it relates to wall constructions is defined largely in Chapter 14 exterior walls as a class 1 or class 2 vapor retarder. So theoretically, any impermeable vapor retarding air barrier is by code correct if it's specified at or less than 1.0 perms. A couple of eagle-eyed, astute specifiers I've seen, because I review a ton of specs, have written their specifications for vapor retarding air barriers to be less than 1.0 perms, again, measured to E96. However, the majority of the industry tend to specify vapor retarding air barriers as a class 1, i.e. less than 0.1 perms. Vapor permeable air barriers are defined in Chapter 2 of the code as any material or construction having a moisture vapor permeance of 5 perms or greater. And again, I've seen a very few sharp-eyed specifiers use that definition when they're specifying vapor permeable air barriers. Again, the majority of the industry tends to default to 10 perms as the minimum threshold for vapor permeable air barriers. So I'm going to move on, but I'm throwing a lot of stuff out here. So these are just some of the terms we'll use periodically. CI for continuous exterior insulation, which is largely required by code. SPF for spray foam, XPS for extruded polystyrene. We don't really go into EPS or expanded polystyrene as we don't see that much in wall construction. And polyiso insulation, which could be either defined as board stock or foamed in place is the correct master format title for that. So what's in a name? These are the many monikers of air barriers. Air and vapor barriers, air and water barriers, air and moisture barriers, weather barriers, weather resistant barriers, AVBs. These are things that just really raise my dander, and I'm not a big fan of it. I really don't like the term vapor in any type of air barrier language. The reason being is that the term vapor, as I mentioned earlier, is something that is technically incorrect. Always start with master format. Master format language is really what should hold sway with specifications. These are just some of the core products that we want to see our air barrier specification titles titled as. So the majority of what we see in the US is fluid applied air barriers. And, the first 4 words are what we see in master format, CSI's master format. The suffix here, the comma, vapor permeable, comma, vapor retarding for fluid applied membrane air barriers, is something that AIA's master spec, it's no longer Deltec, it's Avitru. They've added to their master specifications. And frankly, I tend to like it because when I'm reviewing a spec and I see that title, I know exactly what it is. If I see something that says weather barriers, for example, which I really abhor, I don't really care for that because you have to drill down into part 2, hopefully, to see what the physical properties are that we're specifying. So an interesting heads up. Anyway, air barriers are just that. They are what we should be calling them. They're not air and vapor barriers. They're not moisture barriers. All air barriers are inherently water resistant. So they're basically broken into 2 categories. Air barriers are barriers to the movement of air, but they're either vapor permeable or they're vapor retarding. And again, these are the correct words that we want to use to describe air barriers. So air barriers being the general category, when we're specifying them, we want to specify them as vapor permeable or vapor retarding. I'm going to say one quick thing to this. The very first bullet point on this sheet here is modified bituminous sheet air barriers, which are a pretty fair category for often used. I wish that the folks at Master Format would somehow introduce the term vapor retarding into this type of category. Modified bituminous sheet air barriers are typically a 40 mil rubberized asphalt, typically 36 mils of rubberized asphalt backing, and then a 4 mil high density polyethylene carrier film. So take that for what it's worth. So permeable or non-permeable, which do I specify? I like this graphic on the left because it really lists what permeable air barrier is. I'd like to often use the term or the analogy that a vapor permeable air barrier is much like a Gore-Tex jacket. It stops air and water, but if we're outside raking the leaves and we start moving around, perspiring, that water vapor on our skin now is allowed a means of egress out of that, thus keeping us dry and comfortable. I couldn't find a good graphic for a vapor retarding air barrier, but that's going to be more akin to, say, something like a raincoat, which is going to stop, obviously, air, water, and water vapor getting through that type of material. So permeance decision depends on a number of things. And the first thing I always like to look at is what type of insulation is being used and where is that insulation located within the overall wall assembly. What's the building type? What's its intended use to geographic location? The wall material composition. Is it an all glass curtain wall? Well, if that's the case, then obviously our curtain wall is going to act very much as all four control layers. You know, these paper mills, natatoriums, swimming pool environments are naturally going to be very high vapor loads. So we want to know all this stuff when we're going into deciding what type of membrane to use here. Other driving factors drilling into the insulation. Is it going to be batt insulation? Is it going to be faced or unfaced batt insulation? Is it going to be a open cell? I use the term foam plastic because I am kind of a code snob, as I alluded to earlier. Is it going to be an open cell spray foam, for example, or a closed cell spray foam insulation? And again, where does that insulation layer reside within the overall wall assembly? But we really have to look at virtually everything from the interior finish all the way out to and including the exterior cladding. Systems like insulated metal wall panel systems are pretty much a fully self-contained air barrier, insulation, and cladding system in one material. And that's usually on the outermost face of a wall. I don't know that there would be necessarily any need to have an additional air barrier. I have had architects want to have a redundant system in the event that the insulated metal wall panel systems were to experience a failure. And specifiers in a couple of projects I can recall specified a permeable air barrier in the event that I think they abbreviated them IMPS, were to fail. We still have a plane of air tightness underneath that insulated metal wall panel. So I mentioned the four control layers. Four control layers are air, water, water vapor, and these are often contained certainly in one material, that being the air barrier, and then of course insulation, whether it's rigid insulation or the aforementioned other insulation types. Air, water, and water vapor thermal control obviously can be found in a single material, which i.e. would be a vapor retarding air barrier. And of course, all of these that are bonded to the insulation layer. And of course, in the framed building per the code, we have to have a minimum 7.5, might be actually up to about 10R. Typically at this point. And when we bond those two together, now we have basically our entire environmental separation. And in the case of the perfect wall, and I'm going to refer to anybody who's not familiar with buildingscience.com, their article, The Perfect Wall, is just that, where we have all the insulation placed on the exterior side of the wall. We'll go into that in more detail here in just a little bit. Location of primary thermal layer. First, I want to identify where that insulation layer occurs within the assembly. So if we look at the detail on the left, and I'm going to zoom in on it here. This is, again, from the Building Science article, Understanding Vapor Barriers. This is a framed wall with all of the insulation placed, as mentioned earlier, on the exterior side of our wall assembly. And what makes this the perfect wall is, first and foremost, it's placing the insulation on the exterior side of our wall assembly. And what's important to note about this is the entire structure is effectively now placed essentially on the interior of our building. And as we all know, the structure is the most important element and takes precedence over all other elements. And so if we can protect that structure from the harmful effects of water infiltration, air infiltration, thermal cycling, all things of that nature, we have really a wall that, in my opinion, is likely to be a 100-year wall. But what's interesting here is in this article from, again, the Understanding Vapor Barriers, you'll notice under the Assembly 5, it says applicability, all hydrothermal regions. This wall is arguably probably one of the best walls. And what that means is it can be applied and used in virtually any type of climate zone. Cold climates, mixed humid, hot humid. But notice here, the fourth item down, it says membrane or trowel applied. It's calling it a vapor barrier, class 1 vapor retarder, air barrier, and drainage plane. And that is placed immediately underneath the rigid insulation. But the last item called out here is a latex paint or vapor semi-permeable wall finish. And I mentioned the term vapor semi-permeable earlier, a couple slides back. And the vapor semi-permeable is what is really defined as a class 3 vapor retarder. And interestingly, in the code, it refers to class 3 finishes. These are, again, breathable types of finish, acrylic, enamel paints, for example, perforated wallpaper. And again, we kind of have to jump around different aspects of the code here, but the code in 2015 introduced language that effectively attempts to avoid what is referred to as the, quote, double vapor barrier condition. Something to point out is that if we're using a non-permeable vapor retarding air barriers, as shown in this detail here, we also have to be cognizant of the water vapor permeance of these rigid insulation types here. Basically, any rigid XPS insulation that is 1.5 inches or greater in thickness falls into a class 2 vapor retarder. As a rough industry average, the pink and the blue manufacturers of XPS insulation cite a water vapor permeance at 1.5 inches of about 0.8 perms. If we bump it up to 2, 2.5, or 3 inches, the permeance will not drop for every doubling of the thickness. It's a mathematical deduction, but we're still going to be largely in a class 2 vapor retarder category. So when we marry these two together, we effectively have now our entire environmental separation. The vest is far and away the most expensive wall when we place all the insulation on the outboard side, because now foundations naturally have to get deeper. We have longer tie mechanisms to reach through more insulation to attach the cladding. Something I think has recently changed with the position of these manufacturers of XPS, at least I think in the case of the blue stuff, I can't use product names here, but these manufacturers are moving towards the recommendation of not taping. Yes, they are. The rigid insulation manufacturers are moving away from requiring the taping of joints of the insulation. And always remember that water vapor tends to move from areas of higher concentrations to lower concentrations. And so if our air barrier on this example is going to have the fluid applied and self-adhering vapor retarding air barriers of our world are going to be typically well below 0.1 perms. And so that's going to be easily a low class 1 vapor retarder. And if this is going to be a mid class 2 vapor retarder, the water that might find the lowest permeance, i.e. the air barrier, is always going to find a means of egress towards the area of easier means to getting out of the system. So concerns of water vapor migration is reverse water movement into moisture sensitive materials that might create a longer term drying scenario. I'm reminded of some discussions with one of my CSI colleagues about water vapor migration into these moisture sensitive materials. So if we were to use this wall or even this wall, and we were to specify a vapor permeable air barrier in a particular climate zone that is prone to higher amounts of precipitation, the fact that we have exterior gypsum sheathing, which is water resistant, and we use a untaped XPS insulation, reverse water vapor migration, say in a hot July day, we're dehumidifying on the building's interior to about roughly 30% RH and effectively 100% RH on the outside. We can have water vapor migration through the untaped joints, presumably, and possibly into the gyp sheathing. And the drying scenario, if we look at where the gyp sheathing is in this wall assembly, it's effectively buried within the most centermost portion of this wall assembly, that the drying capability or the ability of that gyp sheathing, which is moisture sensitive, to release that moisture will not likely happen in hours, days, or weeks. In some scenarios, it can actually take months. And I believe one of my CSI colleagues who works in hydrothermal analyses said he had one project where the gypsum didn't release that bound moisture for 3 or 4 months. And coming from the gypsum world, I can certainly attest to the fact that even water-resistant gypsum panels are not immune to constant long-term wetting scenarios. So it's really, again, very important to keep these moisture sensitive materials as dry as possible. So 2 layers are better than 1. So XPS and polyiso insulation are extremely water resistant. More exterior CI equates to a warmer insulation sheathing, moving further away from the condensation. I could get into the discussion about dew point collection. I'm not a big fan of it, and I've actually heard the principal of Building Science Corporation mention it as well. But when we place all of the insulation on the exterior side of our wall assembly, the dew point typically will occur at, around, or generally within the primary thermal insulation. And I'm being somewhat vague. If anybody's been involved in hydrothermal analyses, we watch the dew point occur, again, which is largely going to occur within the insulation. It never occurs in a fixed, static, straight line within the centermost portion of the insulation due to changes in conditions on the exterior. We don't have much change on the interior, but the dew point location tends to oscillate back and forth, and sometimes it might go outside or inside of the rigid insulation, but the majority of its occurrence is largely going to occur within this closed cell, for all intents, closed cell foam plastic insulation. Another interesting fact about rigid insulation is the pink and the blue manufacturers' tech data, which typically cite a maximum amount of water absorption by volume of about 0.1% by volume, as expressed as a maximum. So these are not going to be like sponges and take on moisture and then become basically saturated. I think that argument could be said of expanded polystyrene, that sort of beadboard type of insulation, but I think that might get feathers of those manufacturers a little ruffled as they assert that's not necessarily the case. But the closed cell foam of XPS is very, very minimal in the amount of water that it will uptake. So a wall for all seasons. I don't have, there's a similar wall here, CMU, which is basically the same wall, but really we've used this wall, believe it or not, in mixed humid and hot humid climates. And it does tend to cause confusion with a lot of contractors who are long used the vapor permeable air barriers or the building wraps, which are also very vapor permeable in our world. So then we move on to the hybrid wall. This is also a wall that's said to be applicable for all seasons, all climates. There's a combination of exterior CI and bad insulation between the framing. But again, you'll notice in the applicability column, all hydrothermal regions except subarctic and Arctic. In these regions, they do suggest the use of a hydrothermal analysis so that the interior surface of the foam insulation remains above the dew point. So they want to make sure that impermeable vapor retarding air barrier is appropriate. Now, an interesting story about this wall, about 20 years ago, I was involved with an architect in Chicago who were designing an exterior wall for a healthcare project for, I think it was a school in Louisiana on the Gulf Coast, basically climate zone 2. And the wall was exterior steel framing, 6-inch studs, and they had some type of composite exterior cladding. And the team, this was basically this wall without brick veneer, but it was some composite exterior cladding. And being a hospital, they wanted to make sure that they had the wall that best served the building and, of course, the interior use. And they started out with a wall that had larger insulation. They used a 1-inch layer of exterior XPS insulation, and they ran the wall through a hydrothermal. If anybody's familiar with the term WUFI, W-U-F-I, it was one of those hydrothermal wall analysis softwares. And they found that their dew point was occurring largely on average right at the exterior gyp sheathing and rigid insulation interface. So the dew point was occurring mostly on average at that interface. So they wanted to have a vapor permeable air barrier. When we get to 1 inch of XPS insulation, these measure out at about roughly plus or minus about 3 perms and water vapor permits. So this is a permeable material. It's not until you jump to 1.5 inches or greater do you drop into a class 2 vapor retarder. But this project team determined that they were going to specify a vapor permeable air barrier. But somewhere along the line, they thought about increasing the thermal efficiency of this wall. And they said, well, what would be the consequence if we bumped our 1-inch XPS insulation up to 2 inches? So they did, and there was enough money in the budget apparently, so they ran another hydrothermal analysis. And doing that, they found that their dew point got pushed further out into the cavity, away from the framing, again, away from the moisture sensitive materials. And in doing so, they reversed course. And instead of specifying a vapor permeable air barrier, they actually went to a vapor retarding fluid applied air barrier. So having been witness to that was very, very interesting. And in fact, the code does, as it suggests here for this hybrid wall in extreme cold, subarctic and Arctic, they do suggest in anything less than a climate zone 5 that they do recommend using a hygrothermal analysis if you're going to specify a vapor retarding air barrier in what would seemingly be a mixed humid or a hot humid type of environment. Really, the goal is to keep structural wall components above the dew point. Again, whenever we have moisture sensitive materials, obviously I mentioned gypsum, but steel framing is not immune. I have an image of steel studs that were completely rusted out. The whole vertical faces were just rusted. And you can only throw so much galvanization to the framing. So again, you really want to protect those moisture sensitive materials. Choosing vapor retarding air barriers when all the thermal insulation is on the outboard side of the backup, when that exterior continuous insulation is less than 1.0 perms, i.e. meaning it's a class 2 vapor retarder. And again, this urgent need to protect moisture sensitive materials or wall components. Many walls are designed using non-permeable air barriers. And again, we just looked at the hybrid wall with a combination of batt framing in between the studs and a layer of exterior CI. When the exterior CI exceeds that of batt, these are pretty easy to arrive at. The vapor barrier on the warm and winter side of the insulation. Again, I think I touched on this earlier. Class 1, this is from Chapter 14, Exterior Walls of the Code. Class 1 and Class 2 vapor retarders shall be provided on the interior side of frame walls in climate zones 5, 6, 7, 8, and marine 4. So Class 1 and Class 2 vapor retarders are not permitted naturally in climate zones 1 and 2, as my example on that Louisiana hospital project. Class 1 vapor retarders are also not permitted in climate zone 3 or in an approved design using accepted engineering practice for hygrothermal analysis. And again, the code says, prove it to us that this non-permeable air barrier will work in these climate zones, and that this architect did do their diligence and perform these hygrothermal analysis, and in fact arrived at the fact that they could go with a vapor retarding air barriers. They just obviously made sure that their interior finishes also were not vapor impermeable, because we always want to avoid having two vapor retarding or vapor impermeable materials or coatings within the same wall assembly. Again, it's never a question of if walls get wet. They're going to get wet through drive mechanisms based on seasonal heating or cooling. Again, water vapor is always seeking its equilibrium, going from areas of high vapor pressure to lower vapor pressure. And if we have an entrapment condition, never a good situation. I had a project in Michigan where there was a consultant, and this was before the code required exterior continuous insulation. It was a standard framed wall with batt insulation between the framing. And typically in that type of wall, we would have the vapor barrier on the warm side of that batt insulation, the old-fashioned wall, I guess I'll call it. The exterior side of the wall just consisted of exterior gyp sheathing and some type of cladding system. So there's no exterior continuous insulation. But apparently somebody on the project along the way determined, well, instead of using the typical building wrap, which is vapor permeable, the general convention is to use a vapor permeable air barrier on the cold and winter side of the insulation. Someone determined, well, let's use an ice and water type of material. There's like a 40 mil SBS rubberized asphalt material. To me, I think a more expensive option than using the building wrap, which would have been a lot less costly. So not only did they have a vapor retarding air barrier on the cold and winter side of the insulation, again, no CI here, and they also applied their 6 mil poly vapor barrier, again, I'll use that old term, behind the interior drywall. This building was about 6 months into service, and the occupants, this was an insurance company, ironically, and the occupants along the exterior wall noted that every spring, the bottom 6-8 inches of the exterior wall would become notably wet and would literally be bleeding water into the building's interior. And it wasn't until they consulted with this engineering firm, Grand Rapids, who investigated it and found that they did in fact have a double vapor barrier. They had this impermeable ice and water product, which was not necessarily, I guess at the time, dedicated as an air barrier when they should have had a vapor permeable air barrier. So that's, I'm getting ahead of myself here, but that's typically when we would very much want to see a vapor permeable air barrier. So anyway, I've seen a lot of things, sort of like in a certain TV insurance commercial. I've seen that thing or two. So again, avoid the double vapor barrier condition. This is from chapter 14 of the code. This was the passage I mentioned that was added to the code language, that only class 3 vapor retarders shall be used on the interior side of frame walls where the rigid insulation has a perm rating less than 1.0 perms. Again, when you drop below 1 perm, you are considered a quote vapor barrier. The class 3 vapor retarders are, for all intents, breathable, vapor diffuse open, if you will. So when you have a rigid insulation in the wall assembly, an XPS, a closed cell foam insulation, this is basically a vapor retarding material. We want to make sure that everything from that point inward is vapor diffuse open. So just a heads up on that. The passage from the code, and this is actually the updated language. This is the more current passage, and it basically says where class 2 vapor retarders are used in combination with foam plastic insulation sheathing as CI on the exterior side of the walls, the continuous insulation shall comply with this table, and the class 2 vapor retarder shall have a vapor permeance greater than 1 perm when measured to E96. A vapor permeance greater than 1 is not a vapor retardant, it's actually a class 3. So avoid interior side vapor barriers, quote unquote, when the exterior continuous insulation, specifically the XPS insulation, I should clarify, is less than 1.0 perms. Avoid vapor retarding interior finishes. Again, vinyl covered wallpaper that's not perforated, epoxy, oil-based paints. These are all constitute, quote, vapor barrier. Now, there are always exceptions to this. I've had a number of projects that I've assisted with where they have to have a spray down room where they're cleaning things, or maybe it's a laboratory. And they said, yes, we do in fact have, epoxy covered paint. Well, I would challenge that if that's effectively, for all intents, a clean room. We have a clean room drop ceiling, and say you have slab to deck heights of 10 or 12 feet, and the interior space is maybe 10 feet, and you have another 2-foot plenum above the ceiling. It's not likely that the plenum area is going to have that epoxy paint. Also, if the framing happens to be steel framing, or for that matter, CMU, steel framing, of course, have all those little knockouts. And we have outlet boxes and switch boxes. And again, if that area is only restricted to one space in the overall building, but yet all other sides of the exterior walls are not having that type of interior finish, again, water vapor will seek its own equilibrium. So I don't know that I would get necessarily too overthought on that. So just be aware that water vapor will find its way out of the system if those conditions will exist. Always coordinate with interior design team when these types of conditions exist. People often will say, I want a permeable air barrier so my walls can breathe and dry. Drying is good. It's never a bad thing. Choosing a vapor permeable air barrier, typically on a cold and winter side of the insulation. Here we're showing an example of these insulating sheathings. There are a number of manufacturers that make them. They're typically a polyiso board stock bonded to a structural element, like most commonly OSB. And in those cases, we apply our vapor permeable air barrier to the exterior face of that. So now we have basically our entire environmental separation. Be aware, I've had some projects, and thankfully it's less than a handful, but for some unknown reason, some on the project team have wanted to add another air barrier by a second, third-party manufacturer applied to what already is an air barrier. And it usually results in a pretty disastrous result of moisture entrapment. So just be aware of that. But anyway, we want a permeable air barrier typically on the cold and winter side of the insulation where there's no exterior CI. When the perm rating of the exterior CI is above 1 perm, exterior face of the insulated sheathing as we're looking at here. Now, other reasons to choose vapor permeable when the exterior CI material happens to be mineral and the interior side of that type of detail is covered with a vapor retarding single ply roof membrane, i.e. in a parapet. We always want to have one side of the wall vapor diffuse open, so we don't necessarily want to have two vapor impermeable materials. Yes, other areas on this wall probably would benefit from a vapor retarding air barrier, but I've never been too keen to see specifications where we have permeable air barriers in one area and vapor retarding air barriers in other areas. Inevitably, wires get crossed, and unfortunately, the impermeable vapor retarding air barrier gets used where permeable should have been applied, and vice versa. So, other examples, this happened to have been a project in, I think it was Aurora. It was a historical renovation. It was a movie theater built in the early 20th century, and they were doing some additions to the building. The clay tile exterior walls on the left, they were not going to insulate, but they just wanted to protect from moisture, from water, from air infiltration. So they specified vapor permeable air barrier. Again, it was on the exterior side of the wall, just behind the brick veneer we see. But additions to that project involved a CMU backup wall with exterior CI. But again, keeping specifications simplified, they just kept with a vapor permeable air barrier. I'd like to say, though, that there's no objection from us manufacturers if we have all of our insulation on the exterior side of a wall. There's certainly no objection to using a vapor permeable air barrier. There's a lot of information out there that would suggest otherwise, but manufacturers are not typically in the position to say you should use this or you should use this, permeable or non-permeable. Anyway, simplifying air barrier specs where permeable is needed in key areas, but not others. Again, typically like a parapet. Non-permeable single-ply roof membrane and interior parapet. Again, that's a vapor retarding type of system. That, again, would be the decision to use a vapor permeable air barrier. So are the permeable air barriers to be used beneath insulation with perm ratings greater than 1.0 perms? Sure. So when is a permeance value too high? Many building science organizations and manufacturers have studied this, and 50 perms seems to be the ceiling, the high spot for water vapor permeance. 15, 20 years ago, a number of manufacturers were producing at that time highly permeable air barriers. These were typically sheet goods that had perm ratings between 300 and 400 perms, and I believe that they quickly found that that was actually detrimental to the drying because it allowed perhaps a little bit too much moisture into the system. The industry sweet spot for vapor permeable air barriers tends to be between 10 and 33 perms. A prominent building science PhD states that 10 to 20 perms is really the sweet spot. The spun-bonded polyolefin building wraps typically tend to be between 29 and 33 perms in that range. But again, I mentioned in Chapter 2, vapor permeable membranes are defined as a property of having a moisture vapor permeance rating of 5 perms or greater when tested to E96, the desiccant method for permeable air barriers. So again, most specifiers use 10 perms or greater as the threshold, as I touched on earlier. If we're still unsure of choice of permeable versus non-permeable, again, the hydrothermal analysis will certainly earn its keep. Hydrothermal analysis, WOOFy. Many take the safe route and specify vapor permeable air barriers for all their projects. And again, there's nothing wrong with that. We'll see here on the right-hand side, this is showing where the dew point is occurring largely where it's having the majority of its drop within the primary thermal layer. In this example here, it's mineral wool insulation. So that's where we see the moisture raising or lowering. Unique conditions and applications, subarctic and Arctic climates, equatorial climates. Again, I'll reference that project on the Gulf Coast. Walk-in freezers, these analyses are generally advised for out of the ordinary conditions. These are some of the comments from, again, my CSI colleague who I'm surprised he still talks to me because I pepper him with just endless questions about hydrothermal modeling, and does help provide refinements to the original design. However, it is not a guarantee that the system, quote unquote, works. It does not account for application imperfections, and really importantly, does not account for building materials as they age. So that's very important. But I maintain that certain articles, and again, I use the Building Science Corporation's articles. So again, the Understanding Vapor Barriers piece, and also a sort of a companion piece, Hybrid Attics and Hybrid Walls, and The Perfect Wall. These are really very informative pieces, and in my opinion, have taken out a lot of the heavy lifting of showing what walls work largely in many climate zones. So I think there's a lot of really valuable data that's available. But again, hydrothermal modeling shouldn't be dismissed altogether. I just don't believe it should be relied on. When this became a big thing, 15 years ago, it seemed like half of all inquiries we were getting, we were asked, can we provide hydrothermal modeling? Now, this is probably a $15,000 software package, and it takes about a 2-week training course for users of the software to use it. So getting this information usually should be either through in-house folks or a third-party consultant to perform these analyses. It's important to point out that a lot of building materials that we commonly use have interesting vapor permeance properties. Natural materials like gypsum, OSB, plywood, craft facers have a toggling effect or reaction to changes in relative humidity. Gypsum panels of all stripe will vary anywhere from maybe 20 to 40 perms. At higher relative humidity, gypsum will actually increase its water vapor permeance. There are some products out there that are marketed as, quote, smart vapor barriers, and I maintain that we are already building with materials that act as smart vapor barriers. OSB, for example, could be as low as 1.3 to as high as 12 perms. The latter value up to, in conditions up to 85% RH. Craft facing, again, it tends to move around between a class 2 and class 3. This is an interesting chart from the American Plywood Association that shows that 6 mil polyethylene, quote, vapor barriers, whether exposed to 25% relative humidity or 85%, still maintains its roughly 0.03 perms permeance. The same is held for XPS insulation. Interestingly, you'll notice at the bottom. However, when you look at 7/16 OSB or plywood, these have these great toggling effects. So just interesting food for thought there. So common material wall permeance values, again, vinyl covered wallpaper, class 2, unfaced batt insulation, 40 to 60 perms, rigid insulation with foil facer largely being the lowest permeance element in that type of material. Closed cell spray foam is just under 1 perm, i.e. a class 2, and the other materials that we talked about. Always designed for maximum drying. It's never a question of if walls get wet, they will. So if we can put the entire environmental separation on the outside of the wall, leaving the rest of the wall to breathe and more or less condition to the building's interior, again, without a water vapor restrictive interior finish, any incidental moisture that gets between our framing is still allowed to get back to the building's interior because the mechanical systems are always maintaining a set temperature and set humidity. We're roughly 70, 72 degrees F year round, and we're, maintaining between 30 to 40% RH to our building's interior. Compare that to conceivably up to 100% RH conditions and much hotter and colder temperatures on the outside. So keeping the structure above the dew point is probably very, very important. So anyway, I've got a couple other notes here. Damaging effects of bridging. We can do all these wonderful things and design the perfect wall, but don't ever lose sight of the ferrous-based attachment systems, which can make havoc with our thermal values and create condensation issues, etc. So I'm going to close it out now, and I just know that every decisions are driven by a number of factors. Largely start with the insulation and the interior finishes and location and use of the building here. So third-party building science forensic consultants along with manufacturers reps are also good resource. That's about it. We thank you very much for your time.